Hello, MP Calculus students. No meme today, it's just going to be a video. So, the first thing I want to do is make my calculator cam pretty big, because we're going to do these two problems right there. And I'm going to throw a calculator up here for you guys, too. So the way this is going to work is we are going to, let's see, we're going to evaluate, well, the first one is going to be question A on 413, which I'm just going to do up here with you. Regardless of whether you were here yesterday or what you got out of yesterday, integrals can be easily evaluated on your calculator. Just push alpha, F2. I'm going to run through this. I'm recording this so you can watch this a couple times if you need these steps again. Right there, option number 4 is FN int or function integration, something like that. And if you push enter, you will see pretty much this calculator is really nice to you. It just gives you the empty spaces to put all of the right numbers in the right spot. So for this particular problem, we want negative pi going to pi over 2 of 3 sine of 2x dx. Now is a good time to remember a couple things. First of all, this is just this is just the area of a rectangle. So length, or the height of that rectangle, is given by the function 3 sine of x, and the width of that rectangle is this thing we call dx, which is just a tiny little bit of x value. That's the width there. Now if you push enter, the calculator will just tell you what this integral is worth, and it's 3. A good thing for us to do here before we leave this problem is actually to get a good idea graphically of what this is, which will help us review yesterday. If you go into the window, actually go into the y equals menu of your calculator, and let's type in 3 sine 2x. This is also a good chance to remind you that everything in AP Calculus is in radians, so make sure your calculator is in radian mode and keep it there for the rest of this class. If we want to look at this graphically, if you go to the window, just change your x min to negative pi and your x max to pi over 2. And that'll kind of show you exactly what we're looking at here. We're looking for the area under this curve from that x value to the right x value. It's 3 sine of x, so it'll never be anything more than 3 or less than negative 3. So I'm just going to go from maybe negative 5 to 5 on y. So what we are actually asking the calculator when we ask it to integrate, which is what we're doing there, so we're actually looking for the area between this curve and the x-axis. It's a pretty reasonable thing to say that the area of this little hump there is 3. This is negative 3, and this is 3 again. The total sum of that would be the positive 3 we saw in the calculator a minute ago. That's what's going on there. It's an important thing to have a connection right now between graphically what's going on here and what happened when we just pushed the enter on that right there. Let's try another one. Let's try the second one, part B. I'm going to write my answer on here. What's that? I can't see from here. Uh-oh. Yeah, I don't know. Let's see. The next one is negative 5 to 5 of x squared minus 3. So we'll just go back up here, alpha, F2, to bring up this menu right there. Fn int is what we're looking for. Negative 5 to 5 are the boundaries of our integral. And we're looking for x squared minus 3 dx. It's important to put that in there too. And the calculator will just kind of spit the answer out. 53.3 repeating is fine. Yeah, it's a good thing to point out now that later on in this class, we will be doing these without the calculator. There are formulas and processes and ways to find an integral without doing this. But right now, this is the best tool for the job that we have, especially because we're really leaning into this understanding, not so much just a bunch of formulas that you follow method, especially this year. Also, let's just really quickly look at the window and go from negative 5 to 5 this time. Actually, let's go back into y equals first, and let's plug in x squared minus 3. And if we go to the window menu, go from negative 5 to 5. I actually don't know. What is 5 squared minus 3? Probably like 23 or something? Yeah, let's go from like negative 10 to 30. Maybe something like that with a scale of 5. That should let us see the whole thing. There we go. If I could, I'm sure the calculator can find a way to do it, but if I would shade this area in there, and then shade this negative area down there, and then shade this area right there, That's what the integral is measuring. It's the area between that curve. And what's happening there, just to kind of summarize yesterday, what's happening is we're taking that area and chopping it up into infinite number of tiny rectangles. Let's draw a picture really quick of that. I'll get calculator cam out of the way here for you guys, and for you at home watching this video later too. Doing everything, doing a multi-dimensional show today. But don't forget what's happening here is that you are, basically if you have a curve like the one we just looked at, like this, what we're doing is we're finding the area underneath that curve, between some goalposts, and to do that, we're taking that area, like say this little chunk right there, and we're chopping it up into many, 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 many small rectangles that are so small, they just really don't have a width. If you could zoom in on them, blow them up a little bit and take a look at them, they would just be rectangles. The height of that rectangle would be whatever the function is at that time, and the width would be this mystery thing we call dx, which just means a tiny little bit of x. And so now if this is a and this is b, the left and right goalposts, we would call this area the integral from a to b of f of x times dx. And that's kind of a summary of what we did yesterday. We used to have a whole sigma thing for this. We used to do a whole bunch of that. While we're on the topic of summarizing everything, this is equal to the limit as the number of rectangles approaches infinity of your basic sigma notation from I equals 0 to n of b minus a over n times f of all this stuff. The good news is you don't really need to worry about this anymore, because as we start talking about integrals become far more important. So today we're just going to look quickly at a couple of basic integral rules, and we're going to do that by exploring some problems. So for 414, go ahead and put your calculator away because you do not need it without a calculator. We're going to graph and we're going to shade the region under the curve that is represented by all the integrals in that problem right there. And then our job is to rewrite this expression using only one integral. And then we'll use the calculator at the end to verify that our answer is correct. So what we have here, let's just kind of read it really quick and get kind of a cursory understanding of what we're being asked to do here. We have the integral from 1 to 3, the integral from 3 to 8, and then the integral from -2 to 1. And if you did, I think it was the second or third homework problem on the last assignment, there was a problem almost just like this, kind of setting up this idea. If you really think about them, they're a little out of order, but these three integrals kind of just go right together. Like, for example, this last one here ends at 1, but the first one starts at 1. And the first one ends at 3, but the middle one starts at 3. So let's really quickly just doodle a picture of this thing really quick. Thinking about going from -2 to 8, which is kind of the boundaries that I see there. Let's go over here and draw a little quick graph. We're going to go -2 over here on the left side. And let's go to 8 over here on the right. 1, 2, 3, 4, 5, 6, 7, 8, like that. The graph that we're going to actually draw is the graph 9x minus 2, which we see in all three of those integrals, 9x minus 2. It's got a y-intercept of 2 and a slope of 9, which is getting it kind of bulky pretty quick. We can probably just do a decent job of just sketching it. 9x minus 2, 9x minus 2. Let's see. Y-intercept of 2, slope of -9. You know a good way to do this would just be counting by maybe tens. 10, 20, 30, 40. Anyway, because -2 will give us -20 all the way down there. It's got a y-intercept of -2, maybe a little bit less than that. And then it's just a diagonal line, looks kind of like this. It's not really necessary for us to be super accurate about our graph, but it does help to see what's going on there. What's happening is that we have kind of three separate integrals. The first integral, well, it's actually the last one in our list there. That's the integral from -2 to 1, which I could kind of represent on this by kind of using a highlighter to just kind of fill in like this area right there. That's the first integral, the yellow area, you might say, which you'll probably notice is mostly negative. The next part would be the integral from 1 to 3, which I'll use green for, I suppose. Again, just kind of going from 1 to 3, like this. That little chunk right there. And then the last chunk is from 3 to 8, which I'll use blue for. And by kind of making this drawing together, what I hope you're seeing is that this is all just one continuous integral, because the integrals meet up at the point x equals 1, and then again at the point x equals 3. So it's actually really just one integral. We're adding together 3 of these areas, but since there's a complete continuous connection between them, we can easily express this as one integral. It would be the integral from -2 to 8 of that same function. What was it again? 9x minus 2 times dx. Okay, that's it. There's kind of a sub-lesson in here where if you have 2 integrals that are continuous like this, you can just combine them together. Or you can split them apart into many separate integrals, both of which we'll probably have to do in the future for advantageous reasons and different problems. But this is all just one integral. If you put them in order, it kind of makes sense. We probably could have done this just using the beginning problem, but this is just the integral from -2 to 8 of 9x minus 2 dx. We should also spend a second actually figuring out what it's worth, because we have calculators for this. So we can bring our calculator cam up front. We can just really quickly see if we're actually right here. So alpha f2, opening up integration. If we do the big one, -2 to 8 of 9x minus 2 dx, we get 250. Just to confirm this is correct, let's try. We'll type 3 integrals now. Alpha f2, number 4. We'll go from, I'm just going to put it in the same order that it appears in the book, but let's do 1 to 3 of 9x minus 2 plus alpha f2, number 4. The next one is from 3 to 8 of 9x minus 2 dx. And the final one is plus alpha 2 of 2, number 4, -2 to 1 of 9x minus 2. And this should be 250 also. Yeah, hey, cool. Hey, it all works. Cool. Oh, weird. Cool. Oh, cool. Oh. At this stage, here's what I want you to look. Where are we talking about? Okay, cool. You know what we should do? Let's try 415. The integral from 5 to 0 of 4x dx. I'll draw it with you, and then I'll kind of ask you guys to come up with your own conjectures about what you feel like the answer is, but let's draw it right now. It's just the integral from 5 to 0 of 4x, which is just a nice linear line. Once again, I'm going to do this problem kind of off to the side here, maybe not here. Here's 0, there's 5, 1, 2, 3, 4, 5. Let's see, it's 4x, so this would be 60. You would have kind of a line looking like this. 10, 20, 30, 40, 50, 60, like that. Yeah. Let's play a fun little game where I'll give you a few seconds, or I'll give you a little bit of time to think about it and confirm what is this integral worth? Based on the picture that we've just drawn, what is the value of this integral? The area formula for a triangle is a good choice there. I know, they're so loud in the hallway today.
Go there and beat them up.
I'm not going to do that. if you're watching this video after the fact at home or whatever, this would be a good chance to find the area of this triangle using the area formula. But what we should do then, do you guys have an answer written down? What is it?
150.
150? Okay. What we should do then is go to the calculator and see what the calculator thinks. And it's very, very important that we type in it exactly as it's written. The integral from 5 to 0 of 4x dx.
Yeah, Tyler, no.
Which, the number 50, I'm not, is, I don't know how you guys got 150. Do you get 50?
I didn't. I thought we were just doing our stuff.
Oh, I was well. See, this is if everybody was here, we'd do a thing where I would we do an activity about this problem. But since it's a smaller class, I'm recording it mostly anyway. I was doing it the offhand version.
Is it because the 5's on the bottom?
Yeah, what's up, Jeff?
So, yeah.
Yeah.
The area is 150.
Really?
Right? Yeah.
Is it
60 by 5 divided by
60
2.
times 5 divided by 2.
Yeah, that's 150.
Is it 60?
We got one. Doesn't go up to 60. Right. On the graph.
Yeah, right. 5 times 60 divided by 2.
Yeah.
That's interesting. Yeah, why is it not?
Not yet.
Yeah, why is it not 150? Shouldn't it be negative 150?
You ask me.
I mean, it's negative 50. That's the thing.
You know what? I got no words.
Well, the negative part comes from the fact that this integral, I don't know if you guys noticed it or not, but this integral is backwards. Instead of going, usually we go from left bound to right bound. Left to right, we go from 0 to 5. This one has chosen, for some bizarre reason, to go from 5 to 0, which does create the negative thing happening in the integral. I'm not sure why it's 50 and not negative 150. Unless I made a math mistake. What's 4 times 5?
20.
Oh, I'm an idiot. That's why. 4 times 5 is 20, not 60. Because I don't know how to do 4th grade math.
Neither do I.
No, that's all right. That's the thing that happens all the time. So this is not 60 up here, it's 20. That's why.
So how'd you get 60?
I don't know. Now I'm thinking about it. I'm like, why was I thinking 60? I think I was thinking 4 times 15, which is 60. That's what I was thinking. Hey, you know. Anyway, so if you actually find the area of this triangle, the area of this physical triangle is 50.
Yeah.
But the calculator will tell you that the answer to this integral is negative 50. And the reason why is because area under the curve is only kind of like half true when it comes to what an integral is. Integrals are more about adding up a bunch of tiny rectangles, and this is asking you to actually add up rectangles from right to left, which actually means you're subtracting rectangles. There's a rule that I'm not necessarily supposed to show you right now, but I'm going to show you anyway because I feel like it's a natural time to talk about it. But if you have an integral from, say, a to b of some function f of x dx, this is equal to the opposite, negative integral from b to a of f of x dx. Oh, and my friends at home will get calculator cam out of the way so you can see what I just wrote.
So the opposites are equal?
Yeah. Basically, if you switch the a and the b, you take the same integral value but make it negative. Right now, the way I want you to think about this is instead of shading in the area from left to right, think about removing the area from right to left. That's the good way to think about this. Is if the letters if the values from a to b are going to the right, you're filling in that area. But if they're going the opposite way, from right to left, then you would be taking that area away. The answer to this question is negative 50, and it's because the 5 and the 0 are swapped. This is not so much adding up a bunch of rectangles inside, it's more of taking them all away. And that's kind of the answer for B. There is an important thing we can summarize that in B too, but okay. 416 kind of summarizes what we just talked about. I'm not super interested in looking at Riemann sums really anymore, ever, to be honest. Unless it's important structurally. I think for 416 I would rather have written down exactly what we just wrote down, so I'm not going to worry about it. I would rather talk about 417 to put a little bow on this and then kind of be done for today. So the mission here is to rewrite each of the following expressions as a single integral. Having a graph to work on helps this, but you don't necessarily need one if you've got kind of a good idea what's going on here. For example, in question A, actually it can kind of help for us to just draw, maybe down in this little space. Oops, uh-oh. I hate when my tablet does this. Oh, no. Oh, it took me over here. Okay. Oh, good. Okay, we're back. It might be a good idea, maybe in this little space down here, just kind of like draw a general function. I noticed that if we're looking at the areas here, I see 1, I see 10, 3, 9, and 3. Might be a good idea to just kind of like make a positive graph that maybe goes to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just put, since none of these problems actually say what the function actually is, let's just draw like a curve or something, maybe something like this. Doesn't really matter what it is, but it will help us kind of have a picture to go by when it comes to building our understanding of what these answers are. This is one of those kind of questions where I can just show you what the answer is, and then after you see the answer, it kind of makes sense backwards a little bit, but let's at least kind of talk about it. So for question A, you're starting with the integral from 1 to 6 of some function. So let's just kind of goalpost from 1, 2, 3, 4, 5, 6 to over there. That's where you start. I'll fill it in. I have the ability to fill in and erase things, so I'll do that up here. That would be the yellow area there. But then we're going to subtract from that the integral from 3 to 6. So we'd get rid of this space from 3 to 6. So it's kind of like this. It's like yellow minus green, if you want to think about it that way. And that's going to leave you with the integral from 1 to 3 of f of x dx, which would be this remaining space down there. So this problem is almost like filling in that yellow area and then subtracting the green area, and you're left with what's purple there from 1 to 3. Again, you can follow that along on the notation pretty well, but the picture helps to kind of get an idea of what's going on there. Question B is really similar. Again, we're starting with the integral from 3 to 10, so I'm just going to put a goalpost at 3 and a goalpost at 10. How about that? There's 3, there's 10. We start with that, and I'll just shade it in yellow maybe. Now to that, we're going to add the integral from 9 to 3. And what might be interesting or jumping out at you is that, again, that's one of those backwards integrals. We always want to go from a low number to a high number, but this one's going from high to low, which means it's kind of backwards. So the way I want you to think about this is, say you start with this integral from 3 to 10, this yellow area here. That's kind of like removing, going from 9 to 3 is kind of like removing the area from 9 all the way back to 3. You'd be getting rid of all this stuff, because this time you're going from right to left, which means you're kind of erasing it. So it's all gone. This would leave you with the integral from 9 to 10 of f of x dx. And again, once you see the answer, I'm doing exponent rules in Algebra 1, and it's kind of the same thing. Once you see the answer, you're like, oh, okay, I kind of get it. Another way to algebraically look at this problem without doing the graph is keep the first one the same, but then kind of apply that rule we just looked at. If you want to replace the integral from 3 to 9 with the negative integral from 3 to 9, like that. Switch out the 9 to 3 with a negative integral from 3 to 9 of f of x dx, and then it becomes almost exactly like the previous problem. You're just subtracting the 3 to 9 chunk from the 3 to 10 chunk, and all that's left is the 9 to 10 chunk. I appreciate everybody being, I know it's like the week before Christmas break and we all want to be on a break, but I appreciate us getting this. This is a cool thing to leave off with because it sets the stage for the rest of the year. And this notation is big. And it's pretty easy to understand too. Once you read it a few times, it's like you get used to seeing it. Question C. This one is more testing to see if you really have followed along with the notation so far. This time we don't really have any points that are on this particular integral, or on our little graph down here. But we could just kind of call some out and write some things down. Like, for example, if I just draw, let's say I say this is C and this is D. So there's your yellow area right there. That's the first chunk, the integral from C to D of some function. Well, the next chunk is E to C, and E is underneath C, so E would have to be like back here or something. I don't know where E is. It could be anywhere, but it's got to be to the left of C. And I think what this is really testing to see is do you see the continuity going on here? Both integrals, well, one integral starts at C, the other one ends at C, so you can actually just put them together. It would be the integral from E to D of f of x. Kind of like that first example we looked at today.
You just like not count the C's at all because
Yep.
there's two C's.
Since these are continuous at C, yeah, you can just put them right together.
It's true.
Yep. Integral from E to D. And question D is previewing an idea that's going to pop up. This is, chapter 4 is titled The Fundamental Theorem of Calculus, and question D is kind of leading you toward that. So what's happening here, we can use the same exact drawing, but just kind of like swap out some of the names. We have an integral from A to x plus h. That would be, in this case, if I get rid of these colors there, that would be the yellow, the full thing, this full distance here. Then we have the integral from just a to x. So let's say this is x right there, and that means that this distance here would be h. Just kind of draw that picture there and kind of leave it. This is it's a visual exercise. This is starting to connect to the ideas that we used to build the definition of a derivative to what we're doing right now with integrals. I mean, the fundamental theorem of calculus basically says that the integrals and derivatives are opposites of each other. That's in a quick note. We have some work to do proving that, but they are. So if we were to now, if you think about this, the green area here would be what's in this second integral. So if we were to subtract these, what we would be left with, we'd have the integral from x to x plus h of f of x dx. Or f of t, sorry. F of t dt, I got my thing switched around. That's it. Right now, with these 4 problems, right now, the goal is just to be able to kind of understand what's going on in these 4 problems. This is kind of like walk away from this week. If you can look at those and, okay, say that kind of makes sense, that's good. You will see problems like this on your AP Calc test. They'll say, hey, here's 2 integrals expressions. What's this equal to? And they'll give you a bunch of them that you have to choose from. As far as question E, when you can combine multiple regions, when can you rewrite them, you really want to look for a few key ideas.
Double.
Yeah, you're looking for things. Yeah, doubles are a good thing to look out for. We had a homework question last night that had an even function, which has symmetry to the y-axis. So you saw a lot of double areas there. A big key idea is continuity. When you have 2 integrals that have the same endpoint and starting point, you can usually really easily combine those together. The same thing happened with question D, and also, I guess, B. Think about subtraction. In questions B and D, the second part, oh shoot, I hate when this happens. I don't know why it does that either. See, now I got to do a bunch of scrolling. In questions B and D, there is a second part that is inside of the first part. In both questions D and B, that second part is all a part of the first part, so you can just subtract it out and think about what's left over. Big things to think about there. And also, I think you should just be aware, I'm just going to write it over here, you should just be aware that the integral from B to A of f of x dx is equal to the opposite of the integral from A to B of f of x dx. That's a really handy trick to be able to do. Helps you out of a lot of interesting algebraic situations too. And that's the end of this video. I haven't looked at the homework problems yet. I'll be honest with you. I rolled in today during third hour. I had a doctor's appointment this morning, so I haven't looked yet. But I'll think about it right now. Let's see.
Winter break.
Winter break? I mean, yeah, that's pretty much it. Just this. Yep. 418, yep. Use a calculator. You don't need a calculator, but calculator or geometry. Yeah. The only tool we have right now for evaluating integrals is the calculator, or if it's a nice geometric shape, like a triangle or something. That's all we got. You better believe there's an absolute... How do I do this without swearing? It's an absolute truckload of formulas out there for evaluating integrals, and they're all nasty. Let's see. 419, feels a good one. General antiderivatives, good idea. 420, differentiation, like those questions too. Don't care about 421.
Oh, 420, I didn't
Do you
even
think
I know,
it's
yeah.
worth it to keep the homework that I've done?
Yeah, I was thinking you guys should just, I don't know, because I haven't checked homework in a long time for this class.
Can you
Um,
just not check last chapter so I can just get rid of this?
I was just thinking you could just turn it, like just drop in the basket. Like your chapter 3 packet, if you had it, or if you had a big pile of papers, just drop them off. I'll take them home and sort through them over break. Not a big deal for me to do that. And honestly, homework, I'm just glancing at it, see if it's done. That's it. Doesn't. Let's see.
The last one, right? You said we didn't have to do the last one.
Yeah, not the last one. Let's see. Yep, I do like 422 very much. I do like 423. 424 is good. 425, I'm kind of over the cone problems.
You said not 421?
Not 421. Actually, 425 is a pretty good because it's all just asking for the area of the cross circular section there, so I like that. And then 426 is the person who formulated the modern definition integral. He decided it was not absolutely necessary that each rectangle have the same width.
Wouldn't it be?
I'm just going to kind of circle this one and say this is a bonus.
Yeah, but wouldn't the answer to it just be no?
Let's see. That's a good. I have not thought about this before. George Friedrich Bernard Riemann, from which we get the name Riemann sum. He's the person who formulated the modern definition of an integral. He decided that it was not absolutely necessary that each rectangle have the same width. They do not even have to be the same type. If they don't even have to be midpoint or left end or right end rectangles, will they still give it? Let's see. Examine the rectangles used. Will they still give? I think they still give a pretty good estimate. I mean, especially if you use more of them. The more rectangles you use, it won't matter if they're left, right, or midpoint or what. If you use a ton of rectangles to evaluate that, you will get the same thing, I think. I think they will. I think so. I'm going to put that down. I think it's important, there's especially as the number of rectangles, n, especially as the number of rectangles goes to infinity, each rectangle gets smaller and smaller. So I think it will matter less and less if it's a left endpoint or a right endpoint or midpoint. Won't really matter if you're talking about tiny little infinitesimal triangles.
Boom. Just everyone gets a bonus question, right? Let's go.
Look at that, yeah. Nice work. So it won't matter. That's weird the way I wrote that. It won't matter as much. George Friedrich Bernard Riemann. Can you imagine being in the 1820s and not having a calculator? And
Actually, could you imagine being in the 1820s and only living 60 years? No.
40 years. 40 years. Wow. That's four more years for me. I'm done.